Hello and welcome to part 2 of the video series Deep Learning with Apache MXNet. In part 1 we saw what are the discriminative features of MXNet uh, over other existing deep learning frameworks, and we also saw how to install MXNet particularly on Windows, because on Windows its installation may have certain issues, and I discussed those issues, and we actually get everything running after installation of MXNet. And we also actually wrote a hello world to just to explore the ND array. In this particular part, we are going to actually build a neural network for classifying the MNIST hand recognition dataset. The purpose here is not to build the best or optimal classifier for MNIST dataset. The purpose of this video is to learn actually the components of MXNet for building any kind of deep learning model. In this part, we will be building the plain neural network. In the next part of this video series, we will be actually implementing the convolutional neural network for the same kind of data set. So let's dive in and import certain packages that we might need for this. So for example, import numpy as np, then import, for example, matplotlib.pyplot as plt, import maxnet as mx, import from MXNet, import what are the things that we need from MXNet. We need ND array, we need gluon API, which is the most powerful API and handles all the backend processing in MXNet, and we need autograde for automatic differentiation. We also need a neural network from amzn.to. We need NN neural networks. So hopefully all of these things will be available. So let's see. Now what we really need is we need to have some of the data set, the MNIST data set. So let's say the training data, let's say TD, the training data is max.gluon.data.vision.mnist, and we have this training data, train equals to true. So let's have this data, and similarly if we do the same stuff with train equals false, that will be validation data. Just needed to validate our model. So let's write the validation data. Again, validation data is the same thing with training variable as false. So MXNet has no attribute gluon. I just messed up these spellings here. Yeah, it should work. So because I have already run this command on my machine multiple times, the data has been downloaded already and cached in my system, so it ran quickly. On your system, for example, if you are going to run this first time, it may take a while to download this data and save this in these particular variables. So let's see the type of these variables. TD, that's MNIST, that's a MNIST data set kind of model. Let's see what else do we have. TD dot, what kind of for example, do we have a sample and these kind of stuff. So what we can do now is we can transform this data set to for example, in a particular way, that the number of channels, normally the number of channels, they are available in 28 by 28 by 1. MXNet requires the number of channels to be the first field. So we can convert the data by writing, for example, a function. Let me call that define function. Let's say f transform. Let's say this function. It receives data and it transforms the data in such a way that the number of channels attributed becomes first, and it also converts the data from unsigned integer 8 to float 32 and rescales it from 0 to 1. So what we do basically is we will call nd dot, so nd.moveAxis. This function actually moves the axis of this data. So the axis 2, the dimension 2 actually moves to 0. So what happens is 28 by 28 by 1, that value 1 actually moves to the start, and the data will be having then values 1 by 28 by 28. So after that, you can typecast is to as type float 32, and then you can divide that by 255, no problem, and you can return that value. That's the transformation of the data that we really need. So that's our function. Let's call that function on TD. So let me call that as train data transformed as td.transform first, and you have to give the name of the function here, and the name of the function is here, our function name is transform. You have to give that name, and similarly validation data is again validation data dot transform first, and here you have to give the name of the transformer or the function. So that will transform all the data for us. Next, what we really want is to define the batch size. What are the batch sizes of this data? For example, the batch size of the data, let's define batch size as for mini batch gradient descent, let's define the batch size as BATCH, batch size. Let's define the batch size as 64, let's say, or maybe 100 or maybe 50. Let's define it as 50. So that's our batch size. Now let's build an iterator for this particular batch size. Let's split the data into batches and build an iterator using this Gluon API. So train loader, train data loader is max.gluon.data loader, and here I will give the train data, and I will shuffle. So shuffle variable will be set to true, and the batch size will be the batch size that we have defined. So that will build an iterator for us, TL. Similarly, we can build an iterator for validation data. So let me call that as validation loader. So validation loader, data loader, train data, we have validation data, for example, and the same stuff. Now we have everything, the iterators are done. Let's now define our neural network model. So here, let's define the neural network model is model as NN. Remember this NN from Gluon, we imported this NN, neural network. So NN dot, there are several ways to define this. You can define it as a sequential model or at a hybrid sequential model. Let's define it as a sequential to be the most simple model. Sequential, that's it. You can now, for example, write a namespace if you want. That's optional, but it is recommended. So model dot name scope. In that scope, you can go and define your model. For example, NN dot, first of all, I need to flatten my input, then maybe NN dot dense layer with, for example, 128 hidden units, and the activation might be ReLU, and then I can have another layer, for example, NN dot dense, maybe with 64 neurons, and the activation can again be ReLU, and then I can have another dense layer, for example, with a number of hidden units as 32, activation as ReLU, for example, and then I can have finally the final layer which has total number of units as 10 as the total number of classes I really want. And here I do not define an activation. I will actually define softmax layer in the loss function. So no activation. I can explicitly tell no activation because the loss function that can contain the softmax activation as well. So I can explicitly define none, or I can just simply go and I can just simply omit that thing. So all these things that actually comes under model.add. So it appears actually in model.add function. And here we actually end this add here. So, and then we just, yeah. So that's our model.add. First of all, flatten the input. And then we have first layer with 128 units, then second layer, third layer, and then the final layer. So that's our model. Everything is fine so far. Then what we do is we define whether we are working on a GPU or whether we are working on CPU. For example, in my case, I'm working on CPU. So let's define CTX as max.cpu. And whatever the CPU is available. So for example, if you're working with GPUs, so you might be writing like GPU, whatever the first GPU is, and stuff like so. So that's the CTX that might be required. Now I need to actually initialize my model. So we need to basically initialize the model parameters. So let's initialize the model parameters by writing model.initialize INIALICE model.initialize max.init. There are several ways of initializing. Let's initialize it by Xavier initialization. And what is the context? So the context in my case is simply CPU. So that's how you, sequential object has no attribute initialize. I might have messed with the spellings. Yeah, I here, I guess, yeah. So now you have initialized all the kind of things. Now you have to set, for example, the trainer, and you have to set the loss function, and you have to set the metric, whether it should be accuracy and other things. So let's set the trainer as gluon dot trainer, and the trainer here is basically the trainer here. Params for this trainer is model dot collect params. That's a function for collecting an optimizer. You can have several optimizers to use. Let me use stochastic gradient descent for now, SGD. You have choices here. Then optimizer parameters. There are a lot of optimizer parameters. One parameter is the learning rate. So let's set the learning rate params. There are other parameters as well, but let's set just the learning rate and keep the rest as default. Learning rate, and the learning rate is let's set the learning rate as 0.01. So after that, we are done with defining the trainer. Now we have to define the loss function and the metric. So let's define the metric as max.metric.accuracy. So that's our metric, let's say, and let's define the loss function as gluon dot loss dot soft max cross entropy loss. So Now here, because the loss function itself includes the softmax layer, softmax activation, you need not to define that at the very end if you're using this one. So okay, all set. Now we have our trainer, our softmax cross entropy loss, and now we are ready to actually define the fit function. Like in TensorFlow we have fit function, we have to define the training here. Here the training actually is done with automatic gradient, and remember we have already imported this auto grade, and so let's write a wrapper or basically a driver for training. Let's have number of epochs as, let's say, 5. These are the number of epochs. So for each epoch in range, number of epochs for each epoch, and for each batch. So we will pick a batch, for example, so inputs, and so let's pick a batch like X and Y. X is a batch and Y is its labels. In train loader, remember we have train loader iterator already, so we can have, for example, X as X dot as in the context. The context might be GPU or CPU, and similarly Y is Y as in context, CTX, whatever the context is. Now we have our X, our Y, the labels. Now we are ready to define the backpropagation steps. So with autograde dot record, that is required. The autograde dot record actually saves the computations of the forward pass that are required in the backward pass for updating the parameters. So that's why we are recording the forward pass attributes that will be needed finally when we do the backward pass. So here we have Y hat, or the labels. Y hat is actually model dot input, which model into input, which is X, and then we can define the loss value as our loss function, and we define the loss as outputs, which is the Y hat, and the true labels, which are the Y. So that's our loss. So once we are done with defining the loss and creating all that stuff, we actually can now apply the backpropagation step, which is simply loss dot backward. So that will do the backward pass for, or the backpropagation for this particular batch, and that is a one step. Now what we do, because we have already the backward pass, we will update our metric by giving the true labels as well as the labels that we got. So what accuracy we actually come up with, we update that. And also the trainer will actually make one step of, it will update the parameters, and after updating the parameter, we will again go to the next batch, and we will be doing that batch by batch, like the mini batch gradient descent done. So trainer dot step, and we will take the step as the what is the batch size. So the batch size is really the X dot shape 0, whatever the batch size is. So that's it. That will be done by at every for example, this batch in this training loader, it will train, and finally after completing one epoch, we really want to get our the accuracy. So let's name what is the metric and accuracy, that is metric dot get. So we get that, and we actually can print print the training accuracy, and so we can just simply print the training accuracy. And after each epoch, we have to set our metric. So that's the training phase for this particular. Here we have number of epochs as 5. So let's run this. If it has no errors, it will run properly. So it is running. It may take a couple of minutes for that. So just wait for it and see how it actually print the, for each epoch, it will print the training accuracy. So let's see. Yeah, let's hold on for a couple of minutes for that. Actually, the model has 3 hidden layers, 128, 64, 32. So the computation on my machine is taking time. So the first epoch, after first epoch, the accuracy is 0.73. So similarly, in the second epoch, the accuracy will go higher, and so on for the 5 epochs. So let's wait it to complete for 5 epochs. Yeah, so after 5 epochs, our model actually gave 94% accuracy on the training data, but that's on the training data. What if we want the accuracy on the validation data? So let's do the same stuff for validation data. Let's say metric is max.metric.accuracy. Let's define the accuracy metric for validation data. For X validation and for Y validation. In validation loader, we have XV equals to XV dot as in context CTX, whatever we have defined. Similarly, YV as in context CTX. And now we actually can update our metric. So for example, metric.update with the true labels that are YV and the labels that the model will return on XV for each batch of this. So after this is done, we can actually have name and accuracy as metric.get with this particular function, and we can simply print the accuracy on the validation set. So let's see what it does. It may take some time to actually compute that. So accuracy basically is 94% on the validation set. So that's beautiful, because the accuracy we get on training data actually reflects something on the validation data, which means we are away from the overfitting, at least for now. So that's how you actually build a neural network in MXNet. It is highly flexible. Here you can apply a lot of debuggings and stuff. You can use the hybrid model. For example, here you can use hybrid sequential to speed up things. For example, maybe after 1 or 2 epochs, if you see everything is working fine, you can apply the max.hybridize, which will make these things very, very fast and stuff like so. So I think you have liked this video. In next part, we are actually going to solve the same problem using convolutional neural networks, exactly like we did in TensorFlow. So hope to see you in the next part of this video series.